All right, let's talk about a huge promise in the world of AI. We've all heard it, right? We can take these gigantic, powerful models and prune them, snip away all the unnecessary parts to make them smaller and way more efficient. It sounds like the perfect answer for getting AI to run everywhere. But what if I told you that most of the time, these so-called smaller models aren't actually any faster at all? Yeah, let's dig into why that is.
And this quote right here, it just got straight to the point. This is the central mystery, the sort of uncomfortable truth we're going to unpack in this explainer. It highlights this massive gap between what looks good in a research paper and what actually works in the real world. So what is going on here?
So here's the fundamental problem. For years, you'd see these papers come out with incredible results. We remove 70%, 80%, even 90% of a model's parameters, and the accuracy is still great. But then, when engineers go to actually use these pruned models, they see nothing. No speedup, the number of parameters is way down, but the latency, the actual time it takes to get a response from the model, is basically the same.
Okay, to solve this mystery, we need to line up our two main suspects. These are the two big methods that researchers use to shrink models. They're called unstructured pruning and structured pruning. And understanding how they're different is the absolute key to figuring out why one works and the other, well, usually doesn't.
This slide really lays out the whole story at a glance. On one side, you've got unstructured pruning. Think of it like a surgeon carefully removing individual cells. It creates this very irregular, spotty pattern of what's left. Then on the other side, you've got structured pruning. This is more like a construction crew taking out entire rooms or floors of a building. It removes huge chunks, but the parts that are left are still solid and regular. And that difference, as we're about to see, means everything.
So let's zoom in on our first suspect, unstructured pruning. This approach goes in at the most granular level possible. It targets the individual connections, the weights, between neurons and just sets their value to 0. You end up with what's called a sparse matrix, which is basically a spreadsheet that's mostly full of zeros. This is how you can claim something like a 90% parameter reduction, because you've literally zeroed out 90% of the numbers.
So why doesn't this make things faster? Well, think of a GPU like a massive 128-lane superhighway. It's built for huge convoys of data to travel all at once in parallel. Unstructured pruning is like having all the cars on that highway, but telling 90% of the passengers to get out. You have fewer people, sure, but you still have the exact same number of cars clogging up the road. The hardware, the GPU, is not designed to peek inside each car to see if it's empty. It just processes all the cars. It can't take advantage of that random, spotty emptiness.
And this number right here is the brutal reality. After all that work, removing maybe 90% of the parameters, the actual real-world speedup you see on a modern GPU is almost nothing, maybe 5% if you're lucky. It is a shocking result, and it really gets to the heart of this disconnect between theory and practice.
So here's the technical reason, the real culprit. To actually use that spotty sparsity, the computer would need a separate list, an index, telling it where the next non-zero number is. That process of constantly jumping around in memory to look up where to go next is called memory indirection. And for a GPU, it is performance death. It's so slow that it completely wipes out any benefit you might have gotten from doing fewer calculations.
Now let's turn to our second suspect, structured pruning. This is a totally different philosophy. Instead of removing tiny little weights one by one, this method removes entire, meaningful chunks of the model. We're talking about deleting whole neurons, or, in a big transformer model, deleting entire attention heads.
And why does this actually work? Well, let's go back to our superhighway analogy. Structured pruning isn't about emptying seats in cars. It's about shutting down entire lanes of the highway. If you remove 25% of the neurons, you've basically made the computational highway narrower. You have fewer convoys of data, but the ones you do have are still packed and efficient. It's a change the hardware immediately understands and can accelerate.
Okay, so we have a pretty good theory now, but let's look at the hard evidence. We can use these amazing tools called profilers that let us see exactly what the hardware is doing, second by second when it runs these models. It's kind of like putting a stethoscope on the GPU.
And this table, this is the smoking gun. Just look at that top row for unstructured pruning. The number of calculations, the flops, goes way, way down, just like the papers promise. But then look at the latency. It's about the same. And the really telling part is the kernel type. It's still using a dense gem, a big, dense matrix multiplication. The GPU is running the same old operation. But now, look at the structured row. Flops go down, and latency goes down right along with it. And the kernel type changes to a smaller gem. The GPU is fundamentally doing less work.
This all leads us to a really simple but really powerful verdict in our investigation. This is the one rule to remember. If your pruning method actually changes the dimensions, the shape of the matrices in your model, you are going to get a speed up. If all you're doing is poking holes inside the existing shapes, you're probably not. It's as simple as that.
Okay, so mystery solved. But what this really means is that as a field, we've been using the wrong rulers. To make real progress, we have to stop measuring things that sound impressive but don't actually correlate with performance, and start focusing on what really matters in the real world.
It's time to move on from just reporting these metrics. As we've just seen, parameter count and sparsity are just terrible proxies for speed. And look, accuracy is obviously critical, but reporting it all by itself without any performance data gives you a totally incomplete picture. These are the metrics that got us into this mess in the first place.
Instead, this is what we need to be talking about. Throughput. How many tokens per second can you generate? Latency for a single user, which is what matters for chatbots. Energy consumption. And the one that really matters to businesses, the actual dollar cost to run the model. These numbers are tied directly to user experience and the bottom line.
So, where do we go from here? It means we need a whole new playbook. One that doesn't just start with a clever algorithm, but that starts by thinking about the hardware that algorithm is going to run on.
So what is hardware actually like? Well, it's not complicated. It loves things that are predictable, regular, and orderly. It's built to chew through dense, neatly organized blocks of data. So any pruning method that respects these principles, that works with the hardware instead of against it, has a much, much better chance of actually making things faster. And for any researchers out there, here's an actionable plan, a clear experiment you could run tomorrow. Take a model with 80% unstructured sparsity and pit it against one with just 30% structured pruning. Measure the real latency, not just the parameter count. Try pruning the FFN layers. Those are the really expensive parts of a transformer, and see what happens to throughput. And then put the profiler screenshots right there in your paper. That's the kind of work that will push the whole field forward.
When you boil this all down, you get to this one single key insight. We have to change how we think about this. Pruning isn't really about removing parameters. It's about removing entire paths of computation. It's about simplifying the work the hardware actually has to do.
And this really hammers the point home. A cool new algorithm is only half the battle. If you make a change that the silicon, the actual hardware, can't take advantage of, then the job isn't finished. The algorithm and the hardware have to work together.
And that leaves us with a really exciting question for the future, doesn't it? Now that we know how to measure this stuff correctly, now that we're shifting our focus to hardware-aware efficiency, what comes next? What kind of new models, new algorithms, and maybe even new hardware will we invent when we start designing for speed from the ground up? Thanks for joining me for this one.